record the notes every time so that if you're out, you can go back and watch that video whenever you're out. So that will be available, and I'll post that on Canvas every day. Tandem is not a word we use a lot. Anybody know what that word means or have an idea of where you've heard it? Good. Yes, like in synchronization. Like, can you think of like a instance when you might hear it used? Could be. Could be. Bike. You can have a tandem bike. That's a bike with like double seats and the pedals. Like you got to sync up with those. So what this section is going to be covering is the change in the X values and the change in the Y values, or to be more specific, independent and dependent variables, right? So we're talking about functions is what we're talking about. So functions is something you start doing in like Math 1, right? Long ago. And a function is a mathematical relation that maps a set of input values to a set of output values, such that each input value is mapped to exactly one output value. Now, there's a note here, and I have left it. This came from Brian Passwater. I'm going to be honest, I haven't figured out exactly what he's talking about here, but I left it, and I want us to be on the lookout for this. In previous courses, you have learned that you can use the vertical line test for functions. So like if you have a line that you pass through the graph, if it hits only one time everywhere, then that is a function. It says later in this course we will learn that test does not always work. I am going to be honest and tell you that I don't know where it doesn't work. But I do know that they do not accept it as reasoning on the AP exam. So maybe that's what he's talking about. I couldn't find an instance where like the vertical line test fails, like, but and maybe it's like with the polar and the parametric and stuff we don't get into very much. Maybe that's what I'm missing, but it definitely, vertical line test is not accepted as your reasoning on the AP exam. You have to say that each input value has one output value. Is like the way that they're wanting you to word it. And as we start practicing for the AP exam we'll practice some of that there. So the input values, so your input values of a function is called the domain. Did anybody here have Coach Wood? We've reached the point where no one had Coach Wood, haven't we? I think so. So if Coach Wood was here, he would sing "All My Exes Live in Texas" right now, because exes are in Texas and Dallas is in Texas, and Dallas starts with a D, which is for domain, and that's how you remember the exes are domain. He just liked to sing "All My Exes Live in Texas" a lot. But domain is represented by we really don't want to limit ourselves just to the X, because we'll see a lot of instances where we don't use the X for the independent variable. So it's represented by the independent variable. If you want to put over here, usually X, that's fine. But there are going to be some cases. One that we use a lot is time. So a lot of times we'll see T as being our input value. Or when we get to the trig stuff, we'll see theta as the input value because we'll use that for the angles. So we don't want to limit ourselves too much for the X, but at the same time it is X a lot of times. The output values is called the range. And it is represented by the dependent variable. And it's usually y, or they'll use function notation like f of x or g of x or h of x. Okay, so one thing that we're going to really focus on, this is a big emphasis for AP, and I think it should be a big emphasis in math in general, is multiple representations. So whenever we're talking about something mathematical, there are lots of ways we can represent it, right? We can have a graph of a function. We could also have an equation for a function. We could make a table for that function. We don't do it very often, but we're going to have to do it a little bit more in this class. We could write out a description of that function in words, right? So those four representations are graphical, our numerical, which is your table, our analytical or our algebraic, which is your equation, and our, what do they call words? Can't remember. Anyway, words, written out in words, are our four things that we're looking at to represent our function. So when we look at a function, we want to be able to think about what does this equation, what does it tell me about what the graph will look like? What does it tell me about what's happening to the numbers in the table? Those sort of things, right? We're going to think about it in many different ways. So for these, we're looking at a couple of functions where we don't really have a function rule. Like we don't have f of x equals 2x plus 3. So A tells us the function halves each input value and then adds 1. Now we could write a function rule for that if we wanted, right? Halves each input value. Input value is typically your x. Doesn't have to be. We could use a different letter if we wanted to. And then adds 1. So like if I wanted to write a function rule for this, I could call it f of x equals, I'm having my x, so I could either write it this way, 1/2 times x, or I could do x divided by 2. Those would be equivalent to each other. And then adds 1. Now in Math 1, you focus on this a lot. What type of graph is this going to look like if we graph it? It's linear, right? This is a line. This is just regular old y equals mx plus b. That's one reason I decided to do 1/2 times x instead of doing x divided by 2. It looks a little bit more like y equals mx plus b. So now that I am looking at this, what is my y-intercept? 1 right here, because there's my b right there. And then my slope, what is it going to be? 1/2. So that is rise over run. I just go up 1 to the right 2, up 1 to the right 2. I could also go down 1 to the left 2, like this. And then it doesn't have to be just as dots. We don't have to just get whole numbers. We could connect all of our dots there. Oh, I have messed up though, because I didn't read my directions very clearly. This tells me to sketch a graph for -4 less than or equal to x less than or equal to 4. That's giving me a domain, right? Did I pay attention to that domain when I graphed this? I did not. I put arrows on the end, which would mean it goes on forever and ever and ever. What should I have done instead? End them with dots, right? Stop right there at 4. So I really should have, oh gosh, I went my whole line. I really should have just stopped right here because of that domain restriction that they gave us here. And should I use the closed dots like I've got, or should I have like an open circle? How do I decide? It's the less than or equal to, or the right here. And if there's an or equal to, we're going to use the closed dot. That means that point's included. Thank you. Right there. So we can use a closed dot for this. But if we had just less than signs, we'd use those open circles. Okay? All right. This particular graph, it just gives us points. So we've got -4, -1. We're just graphing points. -1, 2. 0, 3, 2, 3, and 4, 1. Now, we don't want to connect these here because the only information they gave us was the table. So it could be that this is all there is. Sometimes you have limited input values, so that could be what we're dealing with here. Okay, just a quick vocabulary review right here because you're going to see some of these on your assignment. An x-intercept of a graph can also be called. Anybody remember a different word for an x-intercept? A zero. Good. I'm going to put that down below. That's not the word I was thinking of. But there are a lot of instances. Typically, it's talking about an equation instead of a graph, if it's the case, but they kind of go hand in hand. So I'm gonna put that down below. There was one other word. Roots, good. So a zero or a root, or in some instances a solution. It's not exactly the same, but it's very closely related there. So sometimes we're just looking at a lot of different features of graphs today, and a lot of times we might be asked to give those pieces of information. So if for A I was asked for a zero or a root, then x equals -2 is my zero or my root. What about for B? There's not one, right? Because these lines are not connected, so we just don't have a zero there. All right, so you definitely talk about increasing and decreasing in Math 3. I don't think we have to talk about concavity. However, Miss Martin might do it anyway. Have you guys seen that word concavity before? I'm pretty sure I don't do it in regular 3, but I think Miss Martin sprinkles a few extra things in there because she knows you guys are coming this way. For this should be something you've kind of seen before, but we may not have talked about it quite in the same way that we're going to talk about it in this class. Okay, so the official definition of a function that's increasing: as the input values increase, the output values always increase. So mathematically, if A is less than B, then f of A is less than f of B. Okay, now something I'm going to do here on this graph so you can kind of understand that definition is something that we haven't looked at probably in this way a lot. Like, let's say that I have a point right here, and let's say that this is like that, our x coordinate right there is A. Just throwing, I could put it anywhere, right? Because A is just a letter. Well, then the coordinates of this point right here would be A and then f of A. So that means like the y coordinate here, I could label that as f of A. We don't represent it like that much before this class. So like if I have B, I'm going to put B over here. There's B. Then the coordinates for this point would be B f of B. And that means f of B would be right here on the y-axis. Just to do one more thing, it's not related to that definition, but so typically, if I wanted to graph this point right here, where my x coordinate is 4, typically I just do 4, 3, right? That's what I would graph it as. But another way you're sometimes going to see this represented is like 4 f of 4, right? And that's not notation we've necessarily seen a lot before this class. So that definition says if A is less than B, that means A is further to the left than B, then f of A, which is the y-coordinate, has to be less than f of B, right? So if A is lower than B, then the y-coordinate has to be lower than the y-coordinate of your b value. So that is going to guarantee that this graph is always increasing, right? And then the opposite is going to be true for decreasing. Important thing to remember for increasing, decreasing, always start on the left side, right? Left to right for that. Now, concavity is easy to talk about generally, right? If something is concave up, it's just like curved up, right? And if it is concave down, it's got like a downward curve to it, right? I could probably have you pick out concave up, concave down if I just gave you some pictures of a graph. But in this class, we are really going to have to talk about rates of change a lot. So, if something is concave up, then the rate of change is increasing. Now, rate of change. What have you heard about a rate of change before? What was it related to when you were learning about rates of change? Math 1 is where you really like hit it big, but you may have heard it in other classes too. Like if I gave you, for example, if I give you this line right here, if I ask you for the rate of change for that line, what would you do? What? It's going to be pretty close to 1, yes. And what are you thinking of? What's another word for like what you're thinking of? Slope, right? So rate of change, we might even make ourselves a note about that. Rate of change would equal the slope of the line. So when we have a straight line, which is really all you've talked about much for rates of change so far, right? Then the slope's the same everywhere, right? It's, you know, this line, Evan estimated that it'd be somewhere close to 1, and he's probably pretty close there, right? Just up 1 over 1, up 1 over 1, up 1 over 1 is close enough. It's not a perfect line, right? There. Here we have a negative slope. But those are straight lines. Now, if I try to talk about rates of change for this graph, is my rate of change constant? Does it stay the same all the time? No, because over here, my graph's a lot steeper than it is here. It's not very steep right here, right? And then it gets steep again. So this is almost like a little preview of coming attractions right here that I'm going to give you for free. One way we can think about rates of change is to think about the slope of what we would call a tangent line. You learned about tangent lines a little bit in Math 3 with circles. So like whenever you're talking about a tangent line with circles, it would be a line that does like this. It just touches at one point, right? That would be a tangent line. So we can make tangent lines to curved graphs. So if I put a tangent line like right here, it would look something like that, right? And then if I moved over a little bit, let me use some different colors. And over here, I put myself another tangent line. It looks something like that. And then if I wanted to do a tangent line right here, well, that tangent line is just like a horizontal line, right? And then, you know, let's try to, we'll be kind of symmetric with this. Right, there's a little tangent line. And about right here, let's do ourselves another tangent line. So one way we can talk about like how steep a graph is to talk about the steepness of that tangent line. Well, if your graph is concave up, look at what's happening right here. I'm going to just make a guess. Okay, I feel like that purple line right there, that's pretty close to a slope of -1. Close. This is a guess, right? It's about -1. If I want to do the slope of that green line, who has an estimate for me for that? What do you guys think? Okay, I think that's a good guess. -2, it really doesn't matter what you say right there, as long as you say a negative number that is lower than -1, right? So -2, -3, that'd be good guesses right there, right? So let's say that's -2. What would the slope right here, Matthew, be of the blue line, the horizontal line, is 0. Okay? And so if we just keep on going with our assumptions here, what's the slope of this little orange line, assuming this is pretty symmetric? That'd be 1. And then my red over here would be positive 2, right? So what we're seeing is my rate of change as I go from left to right, like the slope, how steep that graph is increasing. It doesn't look like it's increasing here because it's getting less steep, right? But if you look at the numbers, the slope is increasing because we're going from -2 to -1 to 0. So those numbers are increasing. But I actually taught this incorrectly once in calculus because I would say that the rate of change is decreasing there. It is not. The rate of change is increasing the whole time. Even though you're getting less steep, the numbers are increasing, right? And so whenever we have a function that is concave up, that means the rate of change of that graph is increasing. And it can look a lot of different ways. This is just a basic parabola right here. But, for example, an exponential function, exponential growth function that goes zoop up really fast, that is another example of something that is concave up. It doesn't decrease any, it's always increasing, but it's concave up. Concave down is going to be sort of the opposite of what we see here. I'm going to draw these in real quick, similar to what we had. If we go from left to right here, like if we do a slope right here, well, that's probably maybe about positive 2. We're just going with the same guesses that we had. And then if we do one maybe about right here, that's probably about positive 1. And then if we go at that maximum point, we'll get 0. And then if we go to this next point right here, now we've got a negative slope, so it'd be maybe about -1. And then if we go right here, get an estimate of -2 there. So my rate of change is decreasing in that case. 2, 1, 0, -1, -2. Those numbers are decreasing. Right? So this is going to be a big thing. And I love it because it sets us up so well for calculus. Because whenever you get to calculus, we're going to learn even more about how this works. All right? Example 2 here is asking you to tell where H is increasing, decreasing, concave up, concave down. Whenever you're talking about concavity, you're going on looks. Does it look like it's curved there? Let me remind you a few things here about your notation on this and how to report like where the function is doing these different things. The biggest thing is knowing how to give a domain where that is happening. So when we're talking about domain, when we talk about domain, what are we looking at? X-axis or Y-axis for domain? X, right? Always X's, right, for domain. So the numbers we report have to come from the X-axis. One of the biggest mistakes I see kids make, particularly around like this point right here, is they start throwing the Y values in. Like right here, you want to say 3 because the 3's right there next to that point, right? But it's not. That's 0 right there. So what I find most of the time is kids can point to where a graph is increasing, decreasing, concave up, concave down all day long. Where they mess up is writing it down, right? So like, for example, when we're looking for increasing, if I just take my highlighter here and highlight where this graph is increasing. Right here, from left to right, we're increasing. And then from here over to here, increasing, right? Do you guys agree that those are spots where we're increasing? So whenever you are telling me where this is increasing, you need to give the domain where that happens. So you want to look at the X-axis to tell where that happens. You have 2 options on your notation. You need to know both of these. I don't care which one you use, but you need to recognize both because they might give it to you either way on the exam, right? So one option is interval notation. In interval notation, if you want like a closed circle, you're going to use brackets. If you want like an open circle where it's like not included, you're going to use parentheses for that. In this case, we're going to use brackets for these. So we would have from -2 to 0 would be that first section where our graph of h is increasing. The other way to write it is with inequality notation. With inequality notation, if we have brackets or closed circles, we want to use less than or equal to signs. And if we have open circles, we just want to use a less than sign. In general, for increasing or decreasing, unless you have an open circle on the graph, you want to use brackets for those. Good thing is that they don't count off if you accidentally put a parentheses there for increasing and decreasing, unless there was there's a hole in the graph and you used a bracket and you couldn't because there was an open circle. So like here, we would write this as -2 less than or equal to x less than or equal to 0. Use lowest number, less than sign, x, less than sign, highest number every time. Depending on whether you want open circles or closed circles, you'll use those less than or equal to's. Now, that's not our only place where we're increasing. We can use this U right here. That U means union or so it's like we're looking at this part or this part, right? So if we use that U right there, here again we're looking at the x coordinates of the endpoints of this graph. So we would get from 4 to 7, or we could write it for less than or equal to x less than or equal to 7. Okay, so I've talked a lot. I want you guys to try to finish this up. Find the rest of the parts for B through E for me here. And I'm going to freeze the screen right there. So to -2 and 0 to 4. C, concave up, you should get 2 to 7. For D, increasing and concave down is -2 to 0. And for E, you should get 2 to 4. And then I have them written both ways there. If concavity is involved, use parentheses for it. If it's increasing or decreasing, you're going to use brackets for that there. I did see here on this one for D, there may not have been the only one, I did see a -2 to 3, because at this point right here, it's like 3 is right there where you stopped, right? So you just write down the 3, but that's the y coordinate. We want 0, which is the x coordinate of that point. Okay, questions on that? We get 9:55, right? No. 9:50. 9:55. 15 minutes. All right. We can do it. We can do it. Okay. We might have to skip one. We might have to. Okay, we're going to skip a couple, but we can do it. All right. So, graph of K is increasing on these intervals, decreasing on another interval. Then concave up from 3 to 6, concave down from -4 to 3, and from 6 to 7. So, for this, I have a really hard time organizing my thoughts for this. So what I like to do is I like to make myself a little number line over here somewhere. And I like to put all those numbers I see on that number line. All right. So the lowest one I see is -4. Then I've got a 1. I've got a 5. I've got a 7. But then I also have a 3. I'm going to put that in there. I've got a 6. Does that cover everything? I think so. So, what I can do is I can go through and like put increasing or decreasing and then put concave up, concave down in each little section so I know what I'm looking for. So like from -4 to 1, I am increasing. And from 5 to 7, I'm increasing. So I've got increasing here and increasing here. I made it too small. And then decreasing from 1 to 5, so that would be here and here. And then for my concave up and concave down, I'm just going to do like a U, up or down. The graph of K is concave up from 3 to 6. So concave up here and here. And then concave down from -4 to 3. So concave down here, and then concave down from 6 to 7. You don't necessarily have to do this if you're really good at holding lots of information in your mind at once to do this. But this helps me see what's happening. So they don't give us any points on this graph whatsoever. So it doesn't matter where you start. Your graph is going to have the same general shape, but it could go through a lot of different points, right? So from -4 to 1, my graph should be increasing but concave down. So I'm going to start, since I start off increasing, I'm going to start a little lower. I think I'll just start right here. Increasing but concave down over here to all the way over to +1, right? In fact, I'm going to do this. I'm going to put myself some dotted lines. These are not part of the graph, but they are going to help me know when to stop my pieces of the graph. So all these things I've got going on here, I can deal with. So, in fact, I'll color code it here. So let's do this first piece, increasing, concave down, all the way till I get over here. So could look something like this. Then at 1, I'm going to be decreasing, but still concave down. So that would be, let's switch colors. That would be here. At 3, I'm decreasing still, but switch to concave up. So still going down, but concave up. That's my next section from 3 to 5. Then I need to switch to increasing concave up. So I'm going to pick a different color here. What have I not used? There's a pretty one. So increasing concave up. Looks something like that. And then from 6 to 7, increasing concave down. So going up, but curving down. Something like that. There. Now, your graph could look a lot different based like on how high you want to go or low, but you're going to have those same features for those. All right. A quick review, because we've talked about increasing and decreasing, we've talked about concavity, but there is a question on your homework that is going to ask if a function is positive or negative. If a function is positive, then the graph of that function lies above the x-axis. And if a function is negative, the graph of the function lies below the x-axis. So, for example, on this, now yours could be a little different depending on how you drew it. But on this graph that I have drawn, my graph is positive from -4, actually I should use a parentheses there, -4 over to about 3.5. Again, yours could be different depending on how you drew your graph because there weren't such rigid requirements for this. And then It's positive again from, I'm just going to say 6 to 7, but it might be a little past 6 actually there. And then my graph would be negative from about 3.5 over to 6. So you might have a question that asks you about positive or negative rather than increasing and decreasing in concavity. Concavity is going to be, those are going to be the main things asked, but that'll be thrown in. All right, so important things to know. If a function is increasing, then the rate of change of that graph, if you have an increasing graph, if we think about looking back at this picture right here, if it were a straight line, what's the slope of that line? Have to be. It's got to be positive, right? And it doesn't have to be a straight line, but the rate of change is going to be positive if the function is increasing. If the function is decreasing, the rate of change is going to be negative. Now, for concavity, if we think about, we really already did this for concavity. If our graph is concave up, rate of change must be increasing, right? And for concave down, the rate of change must be decreasing. And remember, rate of change, you can think about the slope of that graph. And if it's not a straight line, you can think about the slopes of the little tangent lines at those points. Okay, so sometimes they give us questions where they give us information about the rate of change and ask us about the graph. So here's an example with a table. A table is given that describes the rate of change of a function. For which interval is the function increasing and concave down? So this chart that I've just made right here, like we do something very similar in calculus to, like we make it over and over and over and over and over again. If you memorize this chart right here, it'll definitely be to your advantage. It's a little confusing because it's got increasing and decreasing in two different places, and you can get mixed up between the two. But we are looking for, if I use a highlighter here, which interval is the function increasing and concave down. So we're looking for where the function is increasing and concave down. What does that tell us about the rate of change, right? Rate of change should be positive and decreasing. So we're looking for a place where our rate of change is positive and decreasing. Positive and decreasing happens right here. So 1 to 2 is our answer. Okay. If we look at 5, it says for 5, the function g of x is graphed to the right. Give the open intervals where the rate of change of the function is negative and decreasing. So notice here, they told us, I'm going to use a different color highlighter here. Rate of change is negative and decreasing. Let's think about what that means for the function, okay? They're not asking us about where the function is negative and decreasing, but where the rate of change is negative and decreasing. So if my rate of change is negative and decreasing, that means the function itself is decreasing and concave down. So this graph is decreasing and concave down here and only there, right? Because we're concave up here. So that, remember, whenever we're given our values for that, that is going to be from -4 to -1. And that answer choice is B. So you have to be really careful when you're reading these about whether they're asking you about the function or the rate of change of that function, because there is also a correct answer for negative and decreasing, right? Like, but they're asking about the rate of change. We are out of time to do the calculator active questions, but if it says calculator active, I intend for you to use Desmos. I think everybody is very good with Desmos. So you were just going to answer those questions by typing those in. I can't remember if the homework even has the calculator active. No, homework doesn't even have any calculator questions, so you're good. All right, so this assignment is called Two Truths and a Lie. So have you ever had to play that, like, in Get to Know You game, where you got to tell two truths and a lie about yourself? This is the math worksheet version of it. For each problem, it has for each problem, it has 3 statements. 2 of those statements are true. 1 of them is a lie. You are supposed to identify the lie and explain why that one is false. You don't have a lot of room here. What you can do is just like say S3 is false because it should be concave up. Just mark out down or something like that for those. So you are finding the lie on each one of these. There's a couple that are a little tricky. You even got this vase problem at the end that's going to take quite a bit of thinking. We didn't do one exactly like that, but do your best to think of those. The key for